law of chemical equilibrium. And what is equilibrium constant? We will be using again and again. Law of chemical equilibrium is actually mathematical expression of equilibrium constant. So if I am saying equilibrium constant, how we represent equilibrium constant mathematically, that is known as law of chemical equilibrium. So for that, before going to the definition, just see here. If we have a reaction, this is compound A, B compound, C compound, D compound. Okay. Lowercase a, b, c, d, these are stoichiometric coefficients. Okay. If this is the reaction, then equilibrium constant is given by, that is written at the top also. It is given by the concentrations of the products. So whenever you see in equilibrium chapter, or we have done in mole concept also, this represents concentration, that is molarity. Okay, this is concentration. If I say A here, so concentration of A. So here concentration of C. So the equilibrium constant is given by the concentration of products raised to their stoichiometric coefficients divided by concentration of reactants raised to their stoichiometric coefficients. It means if I have same reaction N2 plus 3H2 gives you 2NH3, then equilibrium constant, and remember this C represents concentration. Equilibrium constant in terms of concentrations, because we are using concentrations here. C for concentration. It will be given by products concentration. Here we have only one product, ammonia. So product concentration in square brackets ammonia raised to its stoichiometric coefficient. What is the stoichiometric coefficient? 2. So to the power 2 divided by reactants concentration. Reactants concentration, we have nitrogen and hydrogen, 2 reactants raised to their respective stoichiometric coefficients. For nitrogen, you have here 1 only, which is not written. So you won't write anything. You don't write to the power 1. So instead of writing 1, you will keep it blank. And here 3. So H2 concentration to the power 3. This is what equilibrium constant is given as. And why we talk about it? There is a specific reason. There is significance of it. I will be talking about. First, understand this is law of chemical equilibrium. So if you write this equation and then represent it in simple English, that is known as law of chemical equilibrium. So I'm writing this mathematical equation in simple English at a given temperature. Why? Because if we change the temperature, equilibrium constant will change. The product of concentrations of the reaction products raised to respective stoichiometric coefficients in the balanced chemical equation divided by the product of concentrations of reactants raised to their individual stoichiometric coefficients has a constant value, and this constant value is known as equilibrium constant. So whenever law of chemical equilibrium is asked, you will just write the English version of this equation in plain English. And you will also write this formula. Chemical equilibrium constant can change only by temperature. Otherwise, equilibrium constant will not change. I am repeating. The value of this equilibrium constant can change only if you change the temperature. Otherwise, whatever amount of A, whatever amount of B you take, or you already have D, etc. Okay, it can achieve equilibrium in different manner. Okay, maybe it can take longer time, less time, right? But the value of equilibrium constant will always be same for a particular reaction. For a particular reaction, it will depend only on temperature, not on pressure. Okay, so momentarily it can change by pressure. If you change the pressure, yes, we will be talking about later on how it will change if you change the pressure. If you change the concentration of any product or reactant, then how it will change. Okay, but the value will change only by temperature. The equilibrium constant has constant value at a fixed temperature. For a gaseous reaction equilibrium, remember I said in previous case, this C represents, because we are representing this constant in terms of concentrations. This can be represented in terms of partial pressures also. Just to understand, just to give you a quick idea, suppose you have a container and this is a piston. Okay, this is piston which you can move. Here you have two gases, or suppose one gas only. Okay, and the volume is 2 liters. This volume is 2 liters. And at the moment, the gas has 4 moles. Okay, you have 4 moles of gas and the volume is 2 liters. So what will be its concentration? So concentration of this gas will be moles divided by liters, that is 2 moles per liter. Do you remember the molarity? Can you recall? Number of moles divided by the volume of solution in liters or not?
Yes, sir.
Yes, sir.
Yes.
Right. So molarity basically we have calculated. It is 2 moles per liter. In 2 liter you have 4 mole. In 1 liter there will be 2 moles per liter. That is the concentration. Now suppose you increase the pressure. You increased the pressure. If you increase the pressure and you bring the piston down here, and now the volume say is 1 liter. Instead of 2 liter, it is 1 liter. Now, will the number of moles change? No, number of moles will still be 4. We have not taken out anything. We have not injected anything. It is still 4 moles. So what is the new concentration? Say it is G dash. It is 4 moles in 1 liter. That is 4 mole per liter. So concentration increased. Concentration is double. Normally, if you don't change anything, if you double the pressure, the concentration will be double. Okay. So it means concentration is directly proportional to pressure. If you increase the pressure, concentration will increase. So the same constant Kc can be represented in terms of pressure also. So concentrations in terms of partial pressures. So suppose instead of just one gas, you have two gases here, gas A and gas B. Both concentration will be doubled because now volume will be half. So if you apply the pressure and volume becomes half, the concentration will be double of both the gases, applying the same concept. So we write it in terms of partial pressure for the same equation. It will be Kp. P represents that we are representing this equilibrium constant in terms of partial pressure. Concept is same. The partial pressures of the products raised to their stoichiometric coefficients divided by partial pressure of reactants raised to their stoichiometric coefficients. Same thing. Similar, not same, similar thing. But instead of using the concentration, now what we are using? We are using partial pressure. Why we are calling it partial pressure? Because of two gases are there, total pressure will be created by both, partially by A, partially by B, partially by C, partially by D, when products are also there by all gases. So it is called partial pressure. Now we can calculate the relationship between Kp and Kc from here. You know that PV is equal to nRT. Pressure into volume is equal to number of moles into gas constant into temperature. Now, if I rearrange this one, I write it as P equals to N by V RT. Now, who will tell me what is this N by V?
Molarity.
The molarity.
Good.
Molarity.
Number of moles divided by volume is actually molarity. So you can say for PA, it will be concentration of A. It is molarity of A, that is concentration of A, RT. Because N by V is molarity, number of moles divided by volume, and molarity is concentration. And concentration we represent by square brackets. So for A, it will be square bracket A. For B, partial pressure will be concentration of B, RT. R and T constant. Gas constant is constant. Temperature is same. We are not changing. So we can substitute these values. We can substitute these values for A, B, C, D here. So sometimes this derivation is asked. So you will simply write PC will be equal to concentration of CRT whole to the power C. PD will be concentration of DRT whole to the power D. PA will be concentration of A into RT to the power A. And PB will be concentration of B into RT whole to the power B. Now, obviously, RT we can take out because RT is common. So RT to the power C, RT to the power D, etc. we can take common. So here it will be RT to the power C into RT to the power D. So, and you know that A to the power M into A to the power N is equal to A to the power M plus N from your math. So that's why it will be RT to the power C plus D. Similarly, in the numerator, it will be RT to the power A into RT to the power B. It will be RT to the power A plus B. And then you know that A to the power M divided by A to the power N is A to the power M minus N. You remember that? Okay. I hope everyone knows at least these simple identities. You have done even in 7th, 8th grade. So now use that. So when we use this one, we do two things. This part becomes Kc. And this part will be RT to the power C plus D minus A plus B. A to the power M divided by A to the power N equals to A to the power M minus N. Here M is C plus D, N is A plus B. Now you got very important entity from here. This is number of moles of products minus number of moles of reactants and gaseous. Okay, gaseous, because we are talking about pressure. Pressure can be created by gaseous moles only. So you will consider only gaseous moles here, C plus D and A plus B. It means it is delta Ng, number of moles of product minus number of moles of reactant. And this is the relationship you need to remember. Kp equals to Kc RT to the power delta Ng. In book, it is written as delta N, but I prefer to write it as delta Ng. Otherwise, there is some probability of mistake. You can consider other moles also. These are only gaseous moles. Now, students normally initially make mistakes. Sometimes they write Kc equals to Kp RT to the power delta Ng. So they switch these two, okay? You can just remember that the relationship between Kp and Kc is Priyanka Chopra, okay? Priyanka first and then Chopra, C. Kp will come first, Kc will come afterwards. Write down this particular relationship. You will have to use it multiple times. Kp equals to Kc RT to the power delta Ng. So when we talk about dynamic equilibrium, this is something I have told you, but graphically I want to explain what actually happens. So initially, the concentration of reactants will be maximum. Okay. The concentration of reactants will be maximum because products are not there. So products concentration will be 0. Reactants concentration will be maximum. So if you understand it with this diagram, the concentration of A plus B, the concentration of A plus B means the reactants is higher. So A plus B chart is red one. Okay. The graph is red one. C plus D is blue one. So you see the concentration of A plus B, that is reactants, is maximum initially. And then as the reaction proceeds with time, the concentration of reactants decreases. And because we get C and D produced, the concentration of C and D increases. Okay. At some time, after some time, the rate of both will become equal. Forward rate and backward rate of reaction will equal. It means the concentrations will not change after that. That is this time. Okay. So this is T naught. After this one, the concentrations will not change. Concentration of reactants and products will be constant. So that's why there is some concentration here, which is constant of products, and concentration of reactants will be constant. So it will neither increase nor decrease afterwards. And don't get confused by this point. This is not equilibrium. This is some point where both the concentration, that is concentration of reactant and product, are equal. Okay. So this does not necessarily indicate the equilibrium. This will indicate equilibrium only in those cases where you have one compound only. For example, H2O from liquid getting frozen to H2O solid. So it is 0 degrees Celsius. At 0 degrees Celsius, it will exist as liquid, 0 degrees Celsius liquid and 0 degrees Celsius ice. Just exactly at 0 degrees Celsius. Okay. So yes, at equilibrium, both will have equal quantity, so equal concentration. In that case, yes. Otherwise, don't get confused with this one. This is any time where reactant and product concentration can be same. We are interested in when the concentrations become constant. They don't change. That is the equilibrium. The reaction can start from any side. I take real example of hydrogen and iodine. When they combine, they produce hydrogen iodide. So as we have already talked about that hydrogen and iodide reactants concentration will be maximum initially. Okay. And products obviously nil amount, 0. And then there will be some equilibrium. Here equilibrium. After that, the concentrations will not change. But this graph actually indicates the reaction from other side also. If you start from 2HI, you have only HI. At that time, no products will be there initially. After that, hydrogen and iodine will be produced. So initially in that case, it will be maximum. And when the reaction proceeds, the concentration of HI will decrease. In this case, it is the reactant. And concentration of H2 and I2 will increase because these are the products now. But they will achieve the equilibrium at the same level. Means when they reach the equilibrium, the concentration of hydrogen, iodine, and hydrogen iodide will be exactly same as these are in this case. So in both the reactions, in both the cases, whether you start from hydrogen and iodine or you start from hydrogen iodide, at equilibrium, the concentrations will be exactly same of each constituent. The only requirement is that you should have exactly same amount, 2HI, 2 moles. So whether you start with 1 mole of hydrogen and 1 mole of iodine, or you start with 2 moles of hydrogen iodide, the equilibrium concentrations will be exactly same. Now, because I talked about the reaction from the other side, in that case, what will be the equilibrium constant? The equilibrium constant will be reciprocal of the original one. And it is very easy to understand why. Why the equilibrium constant of the reverse reaction will be 1 by Kc. Because suppose you have N2 plus 3H2 gives you 2NH3. Okay, same example I am taking here. Kc will be concentration of product raised to its stoichiometric coefficient divided by concentration of reactants raised to their stoichiometric coefficient. This is Kc. If I write it in reverse order, then say it is Kc dash. It will be products concentration. Now these are the products raised to their stoichiometric coefficients divided by reactants concentration raised to their stoichiometric coefficient. And obviously this is reciprocal of this one, that is 1 by Kc. You don't need to prove it. You just need to remember that the equilibrium constant of reverse reaction will be the inverse of original equilibrium constant. So if you flip the reaction, it will be 1 by Kc. Now, another point, suppose you multiply the reaction by some coefficient. Not this one. Suppose you have same thing, N2 plus 3H2 gives you 2NH3. And you multiply the whole equation by 2. Okay. So in that case, it will be 2N2 plus 6H2 gives you 4NH3. 3. So in first case, when I am considering only this one, Kc will be ammonia concentration raised to the power 2 divided by nitrogen concentration whole cube. Now consider this. In this case, say it is K double dash. Now in this case, it will be NH3 products concentration raised to power 4 divided by N2 concentration whole square, hydrogen concentration whole 6, multiplied by their stoichiometric coefficient, which is exactly square of this one, which is NH3 whole square divided by N2 H2 whole cube whole square. That is K square, or you can say Kc square. So if you multiply any equation by a factor, the new equilibrium constant will be Kc to the power n. So if you multiply it by n, it will be Kc to the power n. These simple points you need to remember. So summary of this one given here. If for this reaction, normal reaction, equilibrium constant is K. For reverse reaction, that is products here, reactants here, it will be 1 by Kc. And if you multiply it by n, it will be Kc to the power n. So the factor will go in the power. Now you can get the answer. Suppose I ask you, suppose you divide by n. Suppose you divide by n. Then what will be the Kc? Can you tell me? Answer is very easy. If you know mathematics, you know the answer. If you divide the equation by a factor n, then what will be the new Kc? Now, division by n is actually multiplication by 1 by n. So it's as simple as that. If I say divide by n, it means what I am doing. This is the reaction. Divide by n means I am multiplying by 1 by n. So it means here n is actually 1 by n. So it will be Kc, say triple dash, Kc to the power 1 by n, because we are multiplying by factor 1 by n. So 1 by n will be in the power. So division is actually multiplication by the factor. So you know, in any case, whether it is multiplication, whether it is division, whether it is reciprocal, and this is what you will be using in questions, numericals, etc. You know what to do. How will you get the new equilibrium constant? Right. So the question here. The following concentrations were obtained for the formation of ammonia from nitrogen and hydrogen at equilibrium at 500 K. So it is given that at equilibrium, nitrogen's concentration is this much, and M is written, it means moles per liter, molarity, moles per liter. Hydrogen concentration 3 into 10 power minus 2 moles per liter. Ammonia concentration 1.2 into 10 power minus 2 moles per liter. Because it is at equilibrium, it will not change. It will remain constant. You have to calculate the equilibrium constant. So apply the formula, equilibrium constant. Okay. Reaction for formation of ammonia N2 plus 3H2 gives you 2NH3. You know that for that equilibrium constant we have been using again and again. So by now you are very much clear this will be the equilibrium constant. Substitute the values. That's it. Ammonia concentration 1.2 into 10 power minus 2 whole square. Nitrogen concentration 1.5 into 10 power minus 2 whole to the power 1. Hydrogen concentration 3 into 10 power minus 2 whole cube. And when we solve it, we get 3.56 into 10 power 2. Okay. And the units. Okay. Units will be according to the equation. This is whole square. So it will be mole per liter whole square divided by, this is molarity, that is mole per liter. And this is mole per liter whole cube. Mole per liter whole cube. Okay. So here you have a square and here you have 1 plus 3, 4. So 2 minus 4 will be minus 2. So the unit will be mole per liter to the power minus 2. that is mole to the power minus 2 and liter to the power plus 2. Minus into minus will be plus here. So that's how you will write the unit. Next. Reaction between acetic acid and ethyl alcohol attains a state of equilibrium in an open vessel, but decomposition of calcium carbonate does not. Why? Because what happens in case of the decomposition of calcium carbonate, we get carbon dioxide. And carbon dioxide will escape out. Okay, so it can't happen in open vessels. The equilibrium can be achieved in open system also, but in that case, there should not be any gaseous reactant or product. So in case of the reaction between acetic acid and ethyl alcohol, if you see, this one is liquid, this one is liquid. This is also considered as liquid. I will tell you when we talk about the homogeneous and heterogeneous equilibria. In that case, aqueous and liquid will be treated as same thing. But there is no gaseous product or reactant in this case. So it can happen in open system. But decomposition of calcium carbonate will produce carbon dioxide. So it must be a closed system. That is the answer here. Next one, at equilibrium, the mass of each of the reactants and products remains constant. Does it mean that the reaction has stopped? Explain. Okay, so no, the reaction does not stop. It continues to take place in the forward as well as backward direction, but at equal speeds. Next question. If concentrations are expressed in moles per liter and pressures in atmospheres, what is the ratio of Kp to Kc for the reaction? So you know the relationship between Kp and Kc. Kp is equal to Kc RT to the power delta Nt. So Kp by Kc, this is what we have to calculate, the ratio of Kp. It will be RT to the power delta Ng. And what is delta Ng? Delta Ng is product moles minus reactants moles, only gaseous, okay. So it will be RT to the power products moles, gaseous moles, yes, it is gas, and we have 2 moles, minus reactants moles, both are gases, so obviously we will consider both 2 and 1, 3. It means it will be RT to the power minus 1, that is 1 by RT. However, your teacher will expect to substitute the values of R and T and get the answer. And why? The reason is, question specifically talks about that concentrations are expressed in mole per liter and pressure in atmosphere. It means you need to substitute that value of R, which is in ATM. Okay. So it means you have to substitute the value of R 1 by RT. You have to say 1 by RT will be equal to 1 by R will be 0.0821. Okay. And temperature 298 Kelvin. So substitute the values, get the answer. Now the next one. The equilibrium constant for the reactions are given K1 and K2 respectively. Then what will be the equilibrium constant for this reaction? And here we will actually apply somewhat Hess law, which you know. Okay, how we can get, using these two reactions, how I can get this reaction? And if you see, we need nitrogen on the left-hand side. We have nitrogen on left-hand side. We need NO2 on right-hand side. We have NO2 here on right-hand side. It means we need to just add these two reactions. So if we add these two reactions, do we actually get the third reaction? Check it. Add all of these. It will be N2 plus 2O2 plus 2NO will give you 2NO plus 2NO2. 2NO will get cancelled. And yes, indeed, we get the final equation. N2 plus 2O2 gives you 2NO2. It means when we add first two reactions, we get the final reaction. In such case, what will be the Kc of this reaction? So sometimes C will not be written, okay? If it is not in terms of concentration or pressure, we are talking about in general. So it is K only. So what will be that K? The answer is very simple. The answer is very simple. However, mathematically you can get it. If you add the reactions, the K will be multiplication of the equilibrium constants. That is K1 into K2. Now you might be surprised why I am saying so. Because if you write the equilibrium constant of this, write the equilibrium constant of this K. It is actually same reaction. These are two same reactions. Okay. We added and we got this. So it will be this one. 2NO means NO whole square into NO2 whole square divided by reactants concentration raised to their stoichiometric coefficients. Now you can rearrange these. You can rearrange these. You can write it as NO whole square divided by N2 and O2. O2 square you have written as O2 only. And second, you have taken NO2 whole square divided by remaining part of this, because this was O square, and NO whole square. Okay, both are same. If you multiply these two, you will get denominator here. Okay. And now you can see that this is K1 and this is K2. K1 will be NO whole square divided by N2 O2. And K2 will be NO2 whole square divided by NO whole square and O2, which you have here. But you don't need to prove it if it is asked. You just need to say if we add the reactions, the equilibrium constant will be product of the two individual equilibrium constants. So write it down somewhere. If we add two or more, it can be K1 into K2 into K3 and K4, okay, and so on. Two or more equations or reactions, then the final equilibrium constant will be the product of all individual equilibrium constants. Okay, so the rule is very simple. If you add, then it will be product. If you subtract, then it will be division. And division denominator will have only those equilibrium constants which equations are subtracted. So understand it. I will be raising everything. Just note down quickly if you want to. So suppose you have equation 1, equation 2, equation 3, equation 4, equation 5, and you get final equation by 1 minus 2 minus 3 plus 4 minus 5. Suppose you get final equation by adding first and fourth and subtracting second, third, and fifth. Then final K will be K1 because you have added this K1 and K4. These will be in numerator. And whatever you have subtracted, these three will be in denominator. So in this case, it will be K1 into K2. Next question. For the reaction, common one, N2 plus 3H2 gives you 2NH3. At 400 K, Kp is given 41. Find the value of Kp for each of the following reactions at the same temperature. For this reaction, it is Kp equals to 41. And this is just flipped version. Inverse of this one is this one. It means here it will be 1 by Kp. That is 1 by 41. Okay, so yes, you will say Kp dash will be 1 by Kp. Then the next one. This one. Here, basically, you have multiplied it by 1 by 2. Or you can say you have divided it by 2. The whole reaction divided by 2. Divided by 2 means 1 by n. So here Kp double dash, say it will be Kp to the power 1 by n. That is Kp to the power 1 by 2. That is square root of Kp. Kp is 41. This one is just multiplied by 2, this one. If you multiply the original equation by 2, you get the third one. So it means in this case, it will be Kp to the power n. That is 41 to the power 2, 41 square.